Thank you, Patrick. Good morning, everybody. My name is Donald Finn. I'm talking here on behalf of the Energy Conversion Group. It's a group of a number of academics at UCD. Specifically, I'm going to focus on our work in the building energy sector, and our expertise really lies in two subdomains. First of all, on energy systems that are used in the building energy sector, heat pumps, space conditioning. Not related, transport refrigeration, but I'll explain why I'm going to talk about that as well. And then I'm going to talk also about looking at the whole building and some work we're doing in that area. So focusing first on the first category, we have done quite a bit of work in the area of heat pumps, mostly through, in this case, supported programs from the European Commission. We've also done work on space conditioning in buildings, and we've worked very closely with transport refrigeration with Thermo King. For those of you who are familiar with heat pumps, you'll probably know that a refrigeration system and a heat pump system is essentially the same technology. It's based on the vapor compression cycle, except for it's got a different purpose. In one case, you're heating. In the other case, you're cooling. Nevertheless, you can also use a heat pump for cooling as well. So really, same technology, just different applications. Looking at our work on heat pumps, we've been involved in two projects. First one was under the 6 framework between 2004 and 2007. That particular project was looking at different heat pump systems using natural refrigerants, so hydrocarbons, ammonia, and CO2. And the work that we did at UCD was basically integrating these systems holistically with the building. So it was developing simulation programs and also control algorithms to optimize these systems. And the same consortium went forward after that with a second project, which was the GroundMed project. That was specified by the European Commission that it should focus on heating and cooling of buildings in Mediterranean climates. And it's a demonstration project. It's over 5 years. You can see the demonstration sites here. There's a number of them. There's 8. And again, we're focusing on the issue of system integration right from the ground through to the heat pump and the building. And we're developing simulation models of the entire system. And we're using these models to develop control algorithms for better system performance and better system operation. And you'll see one point here, the system should have what we call a seasonal performance factor. This is the, rather than the COP, which is looking at the steady state performance of the system, seasonal performance is looking at the integrated COP, including some of the parasitic consumption, such as the pumps and fans associated with the system over an entire season. And the target is to design very effective systems and to operate them through the control algorithms effectively so that their seasonal performance factor is greater than 5 in this case, which really means you have to design for very low temperature heating, high temperature cooling, and also to have very well designed components and to have very good control within the system as well. Another piece of work which we've done is looking at evaporative cooling. This is where we use a cooling tower. This is a prototype cooling tower that we built. And this is used in conjunction with either displacement ventilation or with radiant cooling. That's chilled panels or chilled ceiling panels in buildings. And the hypothesis starting out with is that it was possible to design a cooling tower that could bring you to within less than 2 degrees of the wet bulb temperature, and to try and test this concept in the type of climates that we get in the UK and Ireland, essentially a mild temperate climate. And we achieved that. So essentially what we're doing is, this here represents the building. There's a plated heat exchanger between the primary loop, which goes through the cooling tower, and the building here. And the water normally returns, it's circulated, remember, through chilled panels in the ceiling, and it returns at about 18 to 20 degrees. And then through the primary and secondary system, mainly through the cooling tower itself, it's cooled back down and it's reintroduced to the building at about 15 degrees centigrade. Why do you want to do this? Well, in air conditioning systems, you normally produce chilled water at about 6 degrees centigrade. And the potential advantage of this is under optimized operation conditions, we can get COPs between 6 and about 16. So there is a potential energy saving which is associated with this. And we're continuing with this work now to look at the integration into a building and to see how it performs for different types of buildings in different types of climates. The work we're doing with Thermo King is in the area of transport refrigeration. As I said earlier, it's focused around the vapor compression cycle. Same as with heat pumps. In particular, we're focusing on one particular product line from Thermo King. It's what they call a multi-temperature system. These are trucks which are used for distributing food usually in urban environments where there's a requirement within the truck to possibly have 3 different spaces at frozen conditions, -20, fresh, and chilled products 2 and 7. These containers are configured in such a way that you can really have them in different modes for different days. So you could have where it's split into 3, or you could have 1 single unit. And then these also work in summertime, in wintertime, and they're designed for climates as diverse as, we say, the north of Sweden or Finland or Canada, right down to, let's say, Saudi Arabia, Southern Europe. So you're going through a very, very significant range of climate variations. The technology these use are what we call direct expansion. You can just see here these 3 evaporators which are in the units for cooling. And this is a schematic of the current technology, which is called a direct expansion. This requires quite a significant charge of Freon refrigerant, up to about 15 kilograms, and there's a very significant leakage associated with these systems. And Thermo King know, in fact we all know in this industry, that it's expected by about 2016, 2017, particularly European legislation and also from the state of California in the US, that there will be severe restrictions placed on the leakage from these type of systems. So what we're looking at here is using what we call a secondary working flue. This is something like an antifreeze, which is used for the cooling in the actual containers itself. And then you've got a much reduced primary circuit here, and the charge is reduced from about 15 to approximately 2 kilograms. The other advantage of this is that charge is now all contained within the front unit in the truck, so there's much less chance of damage during operation, and there's a reduction in the leakage in this case. This is a picture of the experimental facility that we've developed at the university. This has been supported by Enterprise Ireland through a collaborative scheme with Thermo King and Enterprise Ireland, and this project has been ongoing for about 5 years. So this shows the test rig we have with the cold room, and this is inside the actual chambers itself, so it's really mimicking what's happening in a typical truck, and this is the direct expansion system and the chilled cooling system that we're using. The second aspect of our work is looking at building related items. So we're doing work with radiant heating, natural ventilation, night ventilation, and we're also collaborating with the electricity research group. It's another research group in UCD on the area of demand supply optimization in buildings. Looking at 1 or 2 of these projects, this is work we did a few years ago looking at natural ventilation in buildings. This is a naturally ventilated building of which we developed a CFD model. We also did some experimental testing, and these are some of the results that we got where we compared experimental and simulated results. We also looked at night ventilation cooling, which is basically cooling the building at nighttime and using this pre-cooling of the building to offset the daily load. And this was a particular building that we looked at, and we developed a model using ESPR, which is simulation code developed at the University of Strathclyde. And these are some of the results between the experimental in blue and the predicted or model data in red in this case. Work we've done on radiant heating, using different types of radiant heating. So there's underfloor heating, wall heating, and ceiling heating, and looking at the comfort issues that you get in the space from these different types of heating systems. The software package which was used for this is called Energy Plus in this case. And finally, this is the work which is just starting now on the whole area of demand response. We're going to focus on 2 areas, commercial buildings and home area networks. There will be 2 PhD students working on these. So one is looking at commercial buildings and how you can reschedule loads in buildings to get a better match between the supply and demand on the electricity grid, and also looking at the same issue within the domestic scenario or situation. So again, to finish up, what I'm trying to do here is give you a flavor of the sort of work we do, and as with the other presenters and my colleagues, we're very interested in possibly having discussions if there's some of these areas that you think may be of interest to yourselves. Thank you very much.